Hey team, this is Mrs. Hunter. I got a request to look at Unit 2, FRQ number 1, Part B. So we haven't reviewed gases and partial pressure and K values for that in a little bit, so this is a good chance. So if we take a look at this problem, it tells us a student puts 0.02 moles of methyl into a previously evacuated 1 liter vessel for 50 K, and the pressure is measured to be that. When the experiment is repeated using 0.02 moles of ethanoic acid instead of the measured pressure is lower than 0.74 atmospheres. The pressure for ethanoic acid is due to the following reversible reaction. Okay, so we're going to get less pressure because this reaction goes back and forth, okay? And kind of a weird looking reaction because both reactants are the same thing. So this is actually the same as if you had said 2CH3COOH yields CH3COOH. And what makes this different, it's these two molecules are attached to each other, so it is a different compound. Okay, so assume that when equilibrium has been reached, 50% of the ethanoic acid molecules have reacted. So ethanoic acid, I had in green over here, so this is all to do with this reaction. We had 0.020 moles to begin with, and 50% reacted. So if I cut this in half, I get 0.01 moles that have reacted, or moles that are left at the end. So you can think about it the same either way because it's 50%. Okay, so we have a reversible reaction. I want to know the total pressure. And in this reaction, we have moles, we have the same 1 liter vessel, we have the same temperature conditions. So I can use ideal gas law, right? So I'm going to use that PV equals nRT. Going to solve for the total pressure, so P equals nRT divided by V. But when I start to plug this stuff in, for the number of moles, in order to figure out total pressure, I need to know total number of moles. And because this is at equilibrium, we're going to need to do, you guessed it, an ice table. But this is a nice and easy one. So, I wonder if I can just copy that equation. Ooh. Let me not get fancy. I don't know how to do that. Okay. So, 2CH3COOH reacts, and we get CH3COOH together. So initially, I have 0.02 moles of this, and I have 0 moles of that. We think of the change, this will decrease by 2x, right, because of that coefficient, and this will increase by a value of x, right, because these change proportionately to one another. So at equilibrium, the total and the reactant side would be 0.020 minus 2x, and the total on this side would just be x. And we actually already know what this is, what our reactant is at equilibrium, right? If you go back here, it says 50% of the ethanoic molecules have reacted, which means that's how much have reacted. That's also, right, 0.02, take half, that's also how much is left. So this is equal to 0.010. So now, can you solve for x? Absolutely. Subtract the 0.02, so you get negative 0.01. Divide by negative 2, we now have a positive 0.005 moles. That is our x value. So x equals 0.005 moles. All right, so what I know, this is how many moles of my reactant I have at equilibrium. This is how many moles of my product at equilibrium. Total number of moles, 0.010 plus 0.005 gives me 0.015 moles. So if you're wondering how they got that on the key, that's how they got that on the key. All right, so now I know total number of moles, so we can go ahead and plug that into our ideal gas law equation. So, number of moles, 0.015. There we go, catching up. Oh, of course, I'm going to run out of room. Going to multiply that by 0.08206. Pretend I put all the units. Yeah, that looks messy. Okay. Please pretend I put all the units because I'm running out of room. Going to also multiply by the temperature, which is 450 Kelvin. And then we're going to divide all this by 1 liter, easy peasy. Okay, and to confirm, when I put that in my calculator, let me confirm I get what College Board gets. Okay, so when I do that, I get 0.5539, etc. Units would be ATM, and they rounded to 2 sig figs because of that 50 % and 0.020 and all the rest. Okay, so 0.055. Now the other method they used, they got 0.55. They got 0.56, so it sounds like you can use either one of those numbers moving forward into part B. Or I should say part 2. All right, so let's start analyzing part 2. Calculate the value of the equilibrium constant Kp for the reaction at 450 Kelvin. Okay, and all of our data right now is at 450 Kelvin, so no big deal. So think back, Kp, right? We're going to have products over reactants, and because we're dealing with Kp, right, we're dealing with partial pressures. So if we go back on that other screen, look at the equation we wrote. That's kind of the more simplified one. All right, so we have our products over our reactants, and because there's a coefficient of 2, our reactants are going to be squared. So for Kp, we are going to have whatever the partial pressure of our product, so the CH3COOH2, we're going to have the partial pressure of that divided by the partial pressure of our CH3COOH. Now, remember how I said we could combine these and make that 2? So if you have a coefficient of 2 in front of this, this gets squared. So now we need to know what the partial pressures are. If we look back at what we did in part 1, we know the total pressure, right? That's when we added up the moles of reactant, moles of product. Well, now I need to separate those. So we can do that one of 2 ways. The first way is use that ideal gas law and use it twice. So the first time you'll plug in the number of moles for the product. The second time, plug in the number of moles for the reactant, and you'll get the partial pressure of the product and the partial pressure of the reactant. Pretty straightforward. The other way you could do this is find the mole fraction. And this is actually the way that the key is showing you how to do it. So find the mole fraction of each, and then multiply it by the total pressure, and that will give you the proportion of pressure that each gas is contributing to the total pressure. Remember Dalton's law of partial pressure. So I'm going to go to a slide where I have a little bit more room, and I'm going to go ahead and solve it out. I think you'll know how to do the PV equals nRT, so I'm going to solve it out using the mole fraction method just to kind of show you something a little more of a review of gas stuff that we haven't seen in a little bit. Okay, so recall from the ICE table, we found that at equilibrium, we have 0.01 moles of our reactant and 0.005 moles of our product. So to solve for the mole fraction of each of those, okay, for our reactant, we take the amount of reactant we have, 0.010, and divide it by the amount of gas we have total, 0.015. In doing that, we get 0.666 repeating. Okay, and then we can do the same for our product. So when we do that, we have 0.005 divided by the total moles of gas. I should have been using units. Okay, 0.015. And we get 0.333 repeating. Okay, makes sense. These are the two gases involved. If I added these two fractions together, right, 2/3 plus 1/3, we'd get a whole, which should make sense. And this is where on the answer key you're seeing the 2/3 and 1/3 values from. Okay, so the total pressure using our method came out to 0.55. The total pressure using the second method, or the other method that the College Board used, came out to 0.56. I'm going to use the 0.55 value, but the 0.56, right, we're going to get numbers that are just marginally different, and College Board sees your work. So the total pressure was 0.55 atmospheres. That's what we figured out in part 1. So if I multiply, in order to get the partial pressure of the reactant, right, I would multiply 0.55 by 2/3. And when I do that, we get 0.366 repeating again, so I'm going to round to 0.37 atmospheres. We're going to do the same thing to get the partial pressure of our products. So we take the total pressure, multiply it by what fraction of that, what makes up the gas is product, which is 1/3 of that. Okay, so I get 0.183, round to 2 sig figs, I get 0.18 ATM. This is where my answer differs from what's in the key. The key has 0.19 because they used 0.56 because they used the first method of solving to carry through. Again, if you're showing your work, this is not really of consequence. Okay, so now I can take these values and go back and plug them in to our KP, right? So the partial pressure of the product was 0.18 atmospheres. And the partial pressure of the reactant was 0.37 atmospheres. And per the formula, we square it. Going to plug that in the calculator. And when I do that, I got 1.314. And 2 sig figs, I will just round this to 1.3. There's no units on equilibrium constants. The key had 1.4 because, again, this value is different based on what they got for part 1, and that's just because of the method they used to solve. And again, if they can follow your work, no problem. So hopefully this video helped you a little bit, kind of a good review on equilibrium stuff and partial pressure. And I'll talk to you soon. Let me know your questions. And here's a puppy tax if you made it this far. Have a good one.